Hey OSQ, did you receive fan mail?
No, Microsoft Zero. This is can mail. We're on question 2 of the whole channel. Of course, we're not going to be getting fan mail anytime soon. Dear OSQ, is the square root of x continuous over non-negative reals? If so, how? Since it ends at 0, so it can't be continuous after that point. Well, first of all, unnamed questioner, it doesn't matter if an interval ends, because as far as it cares for functions, the domain controls where we care about continuity. So just because once we hit 0, all the negative lands are too scary for the reals with square root, we're still just as continuous with everything leading up to the 0. So that's good enough for us. But, unsurprisingly, your oddly specific question is the same question from Section 17, Question 4, of Kenneth A. Ross's Elementary Analysis, 2nd edition. Now, before we begin going through proving how the square root of x is continuous over its real domain, I want to set some reminders for viewers and readers. To start, remember, number 1, that continuity over an interval is essentially and logically the same thing as saying continuous over any point within some, we'll say, range, right? Some interval, if you're okay saying the word again, right? But that actually is much easier than it seems, because that allows us to then define a point that's just within that interval and not specify which point it is. And so long as you can still go through the proof without getting any more specific than that, then it works out just fine. For questions that you can find similarly in textbooks, I'll very often try and follow the same logical order of thinking I find makes the most sense. Most of the time, from the textbook itself. Sometimes I'll refer to other textbooks, as you'll see later on this channel. But I really appreciate Kenneth's version of this, because he doesn't just focus on the epsilon delta limit not limit, but just the epsilon delta definition that we have. He also comes at it from the set theory definition, the sequence definition. And that is continuity may be proven using any bound, or for better words, contained sequence, or for better words again, or family of sequences that converges to our specified point. I'll go into more detail in the solution, explaining why this is such a critical juncture for our answer, and exactly the magic of a general point within the interval and a general sequence both coalesce into a rather pristine solution. So let's start off by defining some x0. You can almost think of this as like patient 0, or just our original number that we're thinking of. Be any member of the interval 0 and above, right? Any of the non-negative reals. And we're just going to say, let it be that one. Whichever one you're about to say, sure, it could be that too. The whole point is that we're not trying to make it specific, because then we'd have to break it down into cases. That's just going to waste our time. And let's say x sub n is a sequence, right? Very commonly in Mr. Ross's work, we have this notation which indicates a sequence. In other textbooks, you may see it written out similar to a set or an ordered set, like this. For all intents and purposes, this is what we mean by a sequence, right? The entire sequence x sub n is contained within our same interval, right? For all n in the naturals. A little bit of a stanky leg on that natural there, but you get the picture, right? And all that means, and again, your textbook may use a fancy upside down A to mean for all that means is that now I've defined a general sequence, right? Kept within our domain. And I'm now going to say where the limit of this sequence is our particular x0, right? That's the only restriction beyond the domain that we are putting to this, is that think of any sequence in the world that converges to that particular value. We're keeping it as general as possible, so that way, if someone just were to plug in, well, I have a sequence for the number 5, right? Or a sequence that converges to 5. Okay, it's going to work for this too. Now, note, and this is going to be something for the viewers at home or the viewers of this channel who have this textbook. I want you to note, if you turn to page 42, section 8, example 5, we have just sort of matched the conditions of that example. Now, for the sake of keeping this available to everyone, I'm not going to harp on the proof in that example. If you wish to learn more about the proof in that example, ask the question. But otherwise, just note that the result, or I should say, the corollary or the lemma that kind of results from the theorems that led up to this, the result of this example is essentially that if we have some sequence that converges to some s for some non-negative s, then we actually have the ability to say, oh, then the square root of this sequence must converge to the square root of s. Again, if you're curious as to the who, what, when, where, why, or how, ask the question. We're going to use this, and if you have the book, you'll see that it had recommended you take a look at this for this step. But for those of us who don't have this book, we're going to accept this as a lemma that helps us with our proof to work with. So then, since, right, our x sub n converges to some x naught, right, where our x naught is non-negative, right, we said that prior, then using this lemma, right, which we can just use we can just say that's lemma 1, right? By our lemma 1, the limit of the square root of our sequence must converge to the square root of x0. For our generalized sequence xn, meaning any sequence, right? Meaning any sequence xn that converges to our x0. This satisfies our definition of continuity thus the proof is done. And we'll even put a box on it to make us feel a bit more official about it. Now, admittedly, this proof, very wordy. If you were taking this in a class, very, pretty much refer over to here, do this, do that. If you were doing this on an exam, you may or may not have to prove that the limit of some sequence that converges to a non-negative number, that implies that the limit of the square root of the sequence converges to the square root of such number. But again, we're trying to use, especially when it comes to proof-based courses and classes and topics, we want to use the tools that built us up to this point. And I know that that means that for some people, they might have to click on a few more videos or look at a few more references. But at the end of the day, I'd rather have tighter videos, shorter videos, that cover just what's needed. That way, instead of if another question comes up that requires, let's just say, something similar to Section 8, Example 5, if that ever becomes a video, in the future, that it doesn't have to be stated again over and over. I'd rather have students have access to snappy solutions when it's not something involving, arithmetic and such like that. When it's a proof-based thing, I want students and learners in particular, right? Don't think of yourselves as students who are in a college or in a school. Think of yourself as a learner who is trying to understand the nature of the beast. And compared to oddly specific question number 1, this was a lot quicker, wasn't it? But again, if any of this seemed a little too hand-wavy, or if any of this seemed too vague, respond in the comments, request for clarity, or perhaps ask a question. And we'll start the chain of getting all of those proofs strung out along this channel. And who knows, maybe one day we'll have something really big to show for it. Until next time, happy studying.